Welcome back. Let's practice evaluating double integrals. All right, so here's our first example. We want to evaluate this double integral. We have the integral from 0 to 1 of the integral from 0 to 2 of x cubed plus x times y plus y cubed dy dx. Okay, so first of all, I want to make this clear. All the double integrals that we will be solving in this video will already be set up. We are going to be focusing on the process of solving and evaluating a double integral. If you want to practice setting up the double integrals yourself, or changing the order of integration with dx and dy and changing the bounds of integration, that will be covered in a different video. Okay, so all the double integrals in this video are already set up and we don't have to change the order of integration. We're going to solve them as they are. And so now let's work on that for this double integral here. The first thing that you want to pay attention to when solving a double integral is what variable you need to integrate with respect to first. And that is determined by the inner integral, the integral on the inside of the double integral, right? Technically, you could draw parentheses around this inner integral because really what's going on here with this double integral is we're taking the integral of another integral. And so this inner integral, we are integrating with respect to y. That is what dy tells us. The outer integral then is where we will integrate with respect to x. But let's just focus on the inside integral for right now. Since we are integrating with respect to y, that tells us that these bounds of integration are values of y, and then the bounds of integration for the outside integral will be values of x, since we will be integrating with respect to x for that integral. And what it means for us to integrate a multivariable function in terms of x and y with respect to y is to integrate y but treat x as a constant. So this first term here, x cubed, with respect to y, that is a constant. It's the same as if you had 2 plus xy plus y cubed, or 3 plus those terms. It's just a constant value, so the integral of that constant will be that constant times the variable of integration, which in this case is y. So what we get here first, and we still have that outside integral from 0 to 1, but inside of that what we get is that the integral of x cubed with respect to y is x cubed times y. Then for the second term, we have x times y, where again, x is being treated as a constant. So just think of this term as being 2y or 3y, something like that. The way that you would integrate that term, where you have y to the first power, is to use the power rule of integration. You'll add 1 to that power and then divide by that new power. So y to the first power will become y squared, and then you'll divide by 2. Or the way I'll represent that here is by multiplying by 1/2. We'll have 1/2 times xy squared. Then let's move on to this last term, which is entirely in terms of y, so you can integrate it as you normally would. Add 1 to that power, and then divide by that new power. So you'll have 1/4 times y to the power of 4. But then those three terms will be evaluated from 0 to 2. And then once we do that evaluation, we will integrate with respect to x. So don't forget about that dx on the end. Now, our next step is to evaluate this expression at 2 and subtract the evaluation at 0, but it's important that you remember to plug those values into the right places. Remember that we just integrated with respect to y, so these bounds are values of y, meaning we want to plug them in for y in this expression. So do not plug 2 or 0 in for any of these x's. Only plug them in for the y's. So let's do that here. We have the integral from 0 to 1 of this expression evaluated at 2. So let's plug 2 in for each of these y's. You'll have x cubed times 2 plus 1/2 times x times 2 squared plus 1/4 times 2 to the power of 4. Then you will subtract evaluating this expression at 0. But now notice if you plug 0 in for y in each of those terms, each term is just going to become 0, so that whole evaluation will be 0. So I will represent that by just subtracting 0, but I'm not going to write out each individual term with 0 plugged in for y. You will just get 0 in the end, okay? So then that's still multiplied by dx, and then let's simplify what we have here. This will be equal to the integral from 0 to 1 of 2x cubed plus 1/2 times x times 2 squared. 2 squared is 4 times 1/2 is 2. So we have plus 2x plus 1/4 times 2 to the power of 4. 2 to the power of 4 is 16, and 16 times 1/4, or 16 divided by 4, is 4. So we have plus 4. Okay? And now you'll notice what we are left with here is just a Calc 1 definite integral. The function that we are integrating is entirely in terms of x. We're integrating it with respect to x, which means that these bounds of integration are also values of x. All right, and so our next step is to integrate this function with respect to x. So let's do that. I'll continue my work up here. This will be equal to these terms integrated with respect to x. Starting with the first one here, add 1 to the power of 3, and then divide by that new power, which will be 4. So we have 2x to the power of 4 divided by 4, plus the integral of 2x. So add 1 to that power and divide by that new exponent, and you'll have 2x squared divided by 2, and then you want to integrate 4, and the integral of a constant is just that constant times the variable of integration. So we have 4x, and all that is evaluated from 0 to 1. Okay, and so we will evaluate this at 1 and subtract the evaluation at 0, but real quick, just a couple simplifications that we can make. These 2's cancel out, and 2/4 reduces to 1/2. So this is equal to 1/2 x to the power of 4 plus x squared plus 4x, and that's evaluated from 0 to 1. But now evaluating at 1, we will get that this is equal to 1/2 times 1 to the power of 4 plus 1 squared plus 4 times 1. And then you want to subtract plugging in 0, but again, notice if you plug 0 in for each of these terms, all of them will become 0, so all of those zeros added together is also 0, so we're just subtracting 0. Okay, but then simplifying what we have here, this will be equal to 1/2 plus 1 plus 4, which is equal to 11 halves. That is the evaluation of this double integral. Let's take a look at another example. Here we want to evaluate this double integral. We have the integral from 0 to the natural log of 4, of the integral from 0 to the natural log of 3, of e to the power of x plus y times dx dy. Okay, so notice that for this double integral, the order of integration is different. Last time we integrated with respect to y first and then x, but this time it's x, then y. That's okay. You just want to make sure to identify which one is first and which one is second. And so since dx comes first, we know that we will be integrating this expression with respect to x. And so these bounds of integration are values of x. And then once we've evaluated at those bounds, we will integrate with respect to y and evaluate at these bounds of y. And so let's start by integrating this expression with respect to x. And it looks a little tricky at first, right? We have e to the power of x plus y. That plus y can throw you off, but remember, when we integrate with respect to x, we're going to treat y as a constant. So think of it like this. Instead of e to the power of x plus y, just imagine that it's e to the power of x plus 2. How would you integrate that expression with respect to x? You might think you have to use u substitution by setting u equal to that power, but you can actually avoid u substitution here. You could split up that power and have e to the power of x times e squared, or e to the power of 2, because when you have two exponential expressions with like bases and you multiply them, you add the exponents. So we're just doing the reverse here. And then e squared is just a constant, so you can integrate e to the power of x as you normally would. So applying that to our integral here, remember that we are treating y as a constant. Here's what we'll have. This will be equal to the integral from 0 to the natural log of 4 of the integral from 0 to the natural log of 3 of e to the power of x times e to the power of y. And then that's multiplied by dx dy. Okay, now that makes it a little bit easier to see how you're going to integrate this expression with respect to x, because now e to the power of y is just a constant. It's a constant multiple for e to the power of x. So what we can do is integrate e to the power of x, the integral of that is just itself, and then keep that constant multiple of e to the power of y. So here's the result that we get. We still have the outside integral from 0 to the natural log of 4, but now integrating that inner integral, we still get e to the power of x times e to the power of y, evaluated from 0 to the natural log of 3. And then you're still multiplying by dy. Now, let's evaluate this expression at these bounds of integration. Remember that these are values of x because we just integrated with respect to x, so we want to plug these bounds of integration in for x in this expression. Doing that, we will have the integral from 0 to the natural log of 4 of e to the power of the natural log of 3 times e to the power of y minus e to the power of 0 times e to the power of y. Okay, now simplifying, e and the natural log are inverse functions, so they cancel each other out. You'll just be left with what is inside that natural log, which is 3, and e to the power of 0 is equal to 1. So continuing my work up here, this is what we get. We have the integral from 0 to the natural log of 4 of 3 times e to the power of y minus e to the power of y, and that's multiplied by dy. And now we have like terms here. 3e to the power of y minus e to the power of y is 2 times e to the power of y. So this would be equal to the integral from 0 to the natural log of 4 of 2 times e to the power of y dy. So now we just have a Calc 1 definite integral. Everything here is in terms of y, so we can integrate 2e to the power of y with respect to y. The integral of e to the power of y is itself, and you'll keep that constant multiple, so this will be equal to 2 times e to the power of y, evaluated from 0 to the natural log of 4. So let's take the evaluation at the natural log of 4 and subtract the evaluation at 0. This will be equal to 2 times e to the power of the natural log of 4 minus 2 times e to the power of 0. Now once again, e and the natural log are inverse functions, so they cancel each other out, just leaving you with that 4, which will now be multiplied by 2. So this is equal to 2 times 4, which is 8. So I'll just write down 8. That's equal to 8. And then we are subtracting 2 times e to the power of 0, which is 1. Anything to the power of 0 is 1. So you have 2 times 1, which is 2, and 8 minus 2 is 6. So 6 is the final answer to this double integral. Next up, we want to evaluate this double integral. We have the integral from -4 to 4 of the integral from 0 to x squared of the square root of 64 minus x cubed dy dx. Okay, so once again, the first thing you want to look for is what variable are you going to be integrating with respect to first. And if you're looking at the inside integral, you can see that we are integrating with respect to y first, right? dy comes before dx. So that means that these bounds of integration are values of y, and these bounds of integration, which correspond to dx, are values of x. And do notice that one of the bounds of integration for our inner integral is an expression involving x. That's okay. Remember that when we integrate with respect to y, we treat x as if it was a constant, so technically you can think of this bound as also being a constant. But furthermore, it makes sense because what that means is that after you integrate this expression with respect to y and evaluate at these bounds of integration, you'll be plugging x squared in, and that will become part of the new expression that you will then integrate with respect to x. So it all works out in the end. It's okay, and it makes sense if you see bounds of integration for the inner integral that involve some variables, specifically the variable that you'll be integrating with respect to second. Okay, but anyway, let's work on integrating this expression with respect to y. At first you might think that's going to be difficult, but if you look at this expression, it's entirely a constant with respect to y. We have the square root of 64, all of that is a constant so far, and then you're subtracting x cubed from 64 underneath that square root, and since we're integrating with respect to y, we would treat that x as a constant. So this whole expression is a constant, meaning that if we integrate it with respect to y, you're just going to take that constant and multiply it by the variable of integration. It's just like if you were integrating 2 dy. The integral of that would be 2 times y. The same thing here, the integral of this expression with respect to y would be that expression times y. So here's what we get. This will be equal to the integral from -4 to 4 of y times that expression of 64 minus x cubed, and that will be evaluated from 0 to x squared. And then you still have dx on the end there, but now we can evaluate this expression at x squared and subtract the evaluation at 0. And since we just integrated with respect to y, we will be plugging these bounds, which are values of y, in for this y. Okay, do not plug x squared or 0 in for x right here. Only plug them in to y. So doing that, we'll have the integral from -4 to 4 of x squared times the square root of 64 minus x cubed, and then you would subtract the evaluation at 0, but if you plug 0 in for y, you'll have 0 times that expression, which will just result in 0. So we would be subtracting 0, but I'm not going to bother to write that. I'm just going to leave it like this. Okay, so it is just x squared times the square root of 64 minus x cubed. And we will now be integrating that with respect to x. All we have now is a definite integral from Calculus 1 that we know how to solve. It looks a little complicated at first, but what we have here is an expression that can be integrated using u substitution. We have this composite function here of the square root of 64 minus x cubed. If you let that inside function, 64 minus x cubed, be equal to u, the derivative of that, which would be a function of x squared, can be found right here within the integral. So let's use u substitution here. We'll set u equal to 64 minus x cubed, that expression underneath the square root, and then take the derivative of that, du dx would be equal to negative 3x squared, right? The derivative of 64 is 0, it's a constant, and then you use the power rule for derivatives on negative x cubed. That gives you negative 3x squared. Now solving for du, you'll get du equals negative 3x squared dx. You get that by multiplying both sides of the equation by dx, but then whatever du is equal to, you want to make sure that you can find that in the integral. And I just see x squared dx, not negative 3x squared dx. So let's divide both sides by negative 3, and then we'll be good to go. We'll have du divided by negative 3 equals x squared dx. And now we can do our u substitution. Let's do it up here. We're going to rewrite our integral entirely in terms of u. You could choose to keep the bounds of integration in terms of x if after you integrate in terms of u, you go back into terms of x. But to keep things simple, I'm just going to change those bounds of integration to be bounds of u. So plug each of those values of x into this expression for what we set u equal to. So for positive 4, you'll have 64 minus 4 cubed, which is 64 minus 64, and that's 0. So the upper bound is 0. And then for the lower bound, we need to plug in negative 4, and negative 4 cubed is negative 64. So you'll have 64 minus negative 64, which is 64 plus 64, which is 128. So that new lower bound is 128. Those are the bounds of integration in terms of u. But then rewriting the rest of the integral in terms of u, we have the square root of u, because we set that inside function equal to u, and then x squared dx is replaced by du divided by negative 3. So we're multiplying by du divided by negative 3. All right, now I'm going to pull out that negative 1/3 out to the front, and then rewrite the square root of u to be u to the 1/2 power. That way it's a little bit easier to see how to integrate that. This will be equal to negative 1/3 times the integral from 128 to 0 of u to the 1/2 power times du. Now this is optional, but one more adjustment that I will make here is to use one of the properties of definite integrals. Remember that for a single definite integral like this, that you can flip the bounds of integration if you also negate the integral. And it would be a good idea to do that here. That way we have the bigger number as the upper bound and the smaller number as the lower bound, while also getting rid of this negative out front. All right, so if we flip the bounds of integration, we negate the integral so that it becomes positive. Okay, so again, I'm just using a property of definite integrals that we learned in Calculus 1, just to make this integral a little bit easier to deal with and quicker to solve. But now, our integral is entirely in terms of u, so we're good to go. We can integrate u to the 1/2 power and work with these bounds of integration without ever needing to go back into terms of x. Okay, so using the power rule of integration, add 1 to this power and divide by that new exponent. So 1/2 plus 1 is 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So we'll have 1/3 times 2/3 times u to the 3/2 power, and that's evaluated from 0 to 128. Now you can pull this 2/3 out and multiply it by 1/3, which will give you 2/9 multiplied by u to the 3/2 power, evaluated at 128, minus the evaluation at 0. So we get 128 to the 3/2 power minus 0, right? 0 to the 3/2 power is just 0. Okay, now 128 to the 3/2 power, you can start by taking the square root of that, right? It would be the same as 128 to the 1/2 power cubed, because you could simplify this by multiplying those exponents, and 3 times 1/2 is 3/2. So if you take the square root of 128, you get 8 square roots of 2. So I'll just write that in here. you would be cubing 8 square roots of 2. And so if you cube that and multiply it by 2/9, you should get 2048 times the square root of 2 divided by 9. And that right there is the evaluation of this double integral. And if you want to know the approximate value of that expression, plugging that into your calculator will give you 321.81 and some more decimals. Okay, but that's it for this example. Let's take a look at the next one. For our next example, we want to evaluate this double integral. We have the integral from 0 to 2 of the integral from 0 to the square root of 4 minus y squared of 2 divided by the square root of 4 minus y squared times dx dy. Okay, so for this double integral, the inner integral tells us to integrate with respect to x first, because dx is listed first and then dy is second. So that tells us that these bounds of integration are values of x, and these bounds of integration for the outside integral, which correspond to dy, are values of y. Now, just like with the previous example, this expression initially looks a little bit intimidating to integrate, but we are integrating with respect to x first, and this expression doesn't have any x's in it, right? It's 2 divided by the square root of 4 minus y squared. When we integrate with respect to x, we treat y as a constant. So this whole entire expression would be a constant. The integral of that with respect to x would just be that expression times x. Okay, so here's what we get. This is equal to the integral from 0 to 2 of 2 divided by the square root of 4 minus y squared times x evaluated from 0 to the square root of 4 minus y squared. And then that's multiplied by dy. And now we want to evaluate this expression at this upper bound of integration, and then subtract the evaluation at 0. And remember, we did just integrate with respect to x, so we are going to be plugging those bounds of integration in for x, not this y. So doing that, we get the integral from 0 to 2 of 2 divided by the square root of 4 minus y squared times the square root of 4 minus y squared. Right? I plugged this upper bound in for x. That gives us this expression right here. And then we would be subtracting plugging 0 in, but if you plug 0 in for x, you'll have 0 times this expression, which is equal to 0. So I'm not even going to bother with that. We really don't even need this parenthesis. This is the expression that we would get, and we want to integrate that with respect to y. And now here's where you need to pay attention. At first, this looks like a pretty complicated expression, but we have this same expression in the numerator and denominator, so those will actually cancel out. They are completely removed from the integral. Anything divided by itself is 1, so those cancel out and they're gone. Which leaves us with a really nice integral. We now just have the integral from 0 to 2 of 2 dy. Okay, so what started out as a seemingly complex double integral has all of a sudden become very simple. So this just goes to show that sometimes the bounds of integration, while they may look scary, actually can result in some nice simplifications, which then lead to nicer integrals than you might expect. Okay, because we're almost done here. Integrating 2, a constant with respect to y, is not too difficult. It's just going to be 2 times the variable of integration, which is y. So this is equal to 2y evaluated from 0 to 2. And so you can evaluate it 2, and then subtract the evaluation at 0, which will just be 0. So this is equal to 2 times 2 minus 0, which is equal to 4. 4 is the value of this double integral. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me in the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. Next up, we want to evaluate this double integral. We have the integral from 0 to pi of the integral from 0 to sine x of 1 plus cosine x times dy dx. Okay, so looking at the inner integral, this time we want to integrate with respect to y first, and then with respect to x for the outer integral. So these bounds of integration are values of y, and these bounds of integration are values of x. And so let's get started. We will be integrating with respect to y first, since dy is listed before dx. So we want to integrate 1 plus cosine x with respect to y. And both of those terms, 1 and cosine x, with respect to y, are constants. So both of them, when we integrate them, we're just going to multiply them by y. So this will be equal to the integral from 0 to pi of y plus y times cosine x. And that is evaluated from 0 to sine x. And that's all multiplied by dx. All right, and so then, since we integrated with respect to y, we're going to be plugging these bounds of integration in for y in this expression. So if we do that, this will be equal to the integral from 0 to pi of y plus y cosine x, where we will replace those two y's with sine x. So we have sine x plus sine x times cosine x, and then you want to subtract the evaluation at 0. But as with previous examples, notice that if you plug 0 in for both of these y's, that both terms will be 0, so you would be subtracting 0, which doesn't do anything. So I'm not even going to include that here. We get sine x plus sine x times cosine x as the integrand for our second integral, which should make sense. We now have an expression in terms of x that we want to integrate with respect to x. And the first thing that I'm going to do is actually split up this integral into two integrals. That way we can work on each of these terms individually, because while sine x is pretty simple to integrate, we just need to use a basic integration rule, sine x times cosine x is a little bit more involved. We will need to use u substitution in order to integrate that. So let's split up the integral here. We will have the integral from 0 to pi of sine x dx, and that will be added to the integral from 0 to pi of sine x times cosine x times dx. Okay, now we'll continue my work up here, but as I said, we do need to use u substitution on this second integral, and it actually doesn't matter which one of these two functions you choose to set equal to u, because the derivative of sine is cosine, and the derivative of cosine is negative sine, so you can make both of those work. However, I will choose to let sine x be equal to u. That way I don't have to work around an extra negative like I would if I set cosine equal to u. Okay, so again, it doesn't matter which one you use, but I'm going to let u be equal to sine. So let's work on that on the side here. U will be equal to sine x. So the derivative of u with respect to x would be cosine x, which works out pretty well. That is exactly what we have in this integral. So we can replace that with du, just make sure to multiply both sides by dx. So I'll just do that right here. We will have that du is equal to cosine x dx. So we will rewrite this integral in terms of u, but first let's integrate sine x. The integral of sine is negative cosine, so this is equal to negative cosine x evaluated from 0 to pi. And then we have our integral that we're now writing in terms of u. And I am going to change the bounds of integration to be values of u as well. So plugging pi in for x in what we set u equal to, sine of pi is 0, and then plugging in the lower bound, sine of 0 is also 0. So this is an interesting result. Both of the bounds of integration become 0, and then the inside of the integral is just u times du. We replace sine with u and cosine x dx with du, but we don't even need to worry about integrating this. As soon as you have two bounds of integration that are exactly the same, in this case they're both 0, the result of that definite integral will be 0. Okay, that's just one of the properties of definite integrals from Calculus 1. So we don't even need to integrate that. We can now solely focus on this evaluation right here. So we have negative cosine x, which we will evaluate at pi, and then subtract the evaluation at 0. So this will be equal to negative cosine of pi minus negative cosine of 0. Now cosine of pi is negative 1, so this is equal to negative 1. And then you are subtracting negative cosine of 0, and cosine of 0 is 1. So you will be subtracting negative 1, which will result in plus 1. So this is equal to 1 plus 1, which is equal to 2. So 2 is the evaluation of this double integral. Let's move on to the next example. For our next example, we want to evaluate this double integral. We have the integral from 1 to 4 of the integral from 0 to the square root of the natural log of y divided by y of x times y times e to the power of x squared times y, all multiplied by dx dy. Okay, so there's a lot going on with this integral, but don't let it overwhelm you. Just take a look at what you have to integrate with respect to first. And in this case, we have dx before dy, so that means for the inner integral, we are going to be integrating with respect to x, and then once we integrate and evaluate, we will then work on the outer integral, where we will need to integrate with respect to y. So these bounds of integration for the inner integral are values of x, and these bounds of integration for the outer integral are values of y. Now let's actually work on integrating this expression with respect to x, but that does seem a little tricky, right? Just looking at this expression, it does involve both x and y, so this is not just an easy case of integrating a constant by multiplying it by the variable of integration. That's not the case here. We do have to account for the fact that we have an x out here and an x squared in the power of e. But you still want to keep in mind here that because we're integrating with respect to x, that we are treating y as a constant. So this y and this y are just constants. So just for a second, and I'm not going to keep this here, but if you just cover up those two y's, all of a sudden, this looks like an integral that we know how to solve, right? This is a calculus 1 integral where we can use u substitution. You can set u equal to that power of x squared, take its derivative, and that will be a function of x to the first power that you can find within the integral, and you'll be good to go. It just doesn't look like that at first because those y's are kind of clogging it up. So if you're ever stuck on a particular expression, that's something that I recommend that you try. Whatever variable you're treating as a constant for that first integral, just temporarily cover it up, whether you have to scribble over it or just rewrite the function without it. Whatever you have to do, just try to get a good look at your function, but only in terms of the variable that you're integrating with respect to. Sometimes that can help you get a better picture of what integration method you might want to use. And so we are going to use u substitution here, but I do have to include this entire power. I can't just set x squared equal to u, I have to set x squared times y equal to u. Okay, it's just like if you had e to the power of 2x squared. You still have to set 2x squared equal to u, not just the x squared part. But that's actually going to work to our advantage here, because if we set that power equal to u, that derivative will still involve that y, which we can also find right here within our integral. So the constant parts of the derivative might actually match up, which would be really nice when we go to rewrite that inner integral in terms of u. So let's work on that here. We are going to let u be equal to that power of x squared times y. And then we want to take the derivative of u with respect to x. Now that sort of looks like we have to use a partial derivative here because u is set equal to a multivariable function, which technically that is what we're doing here. But in order for our notation to match up, I'm just going to think of this as if y really is just a constant. So we're going to take the derivative of u with respect to x. I'm not going to use the partial derivative notation, but we are essentially taking a partial derivative here because we're treating y as a constant and differentiating with respect to x. So multiply that power down, subtract 1 from the exponent, and you'll get 2x times y. All right, now solving for du, we have du is equal to 2xy dx. That's just multiplying both sides by dx. And then within the inner integral, we have x times y times dx. I don't see a 2, so I'm going to divide both sides by that 2. So we'll get du divided by 2 is equal to xy dx. And now we have a u sub that's going to work. So let's rewrite the integral in terms of u. This will be equal to the integral from 1 to 4 of the integral, but now we're going to rewrite those bounds of integration to be in terms of u. So we have to plug both of them into this expression for what u is equal to. Now let's start with the lower bound, and remember that these are values of x, so plug it in for x, not y. If x is equal to 0, you'll have 0 squared times y, which is 0. So that lower bound is still 0, but now it's in terms of u. But then for the upper bound, you want to plug in the square root of the natural log of y divided by y in for x in this expression. Now that's a little bit more involved, so I am going to write that out. What that will give you is the square root of the natural log of y divided by y squared times y, and that's equal to the natural log of y divided by y times y, right? If you square a square root, they cancel out, so you're just left with the inside part, which is the natural log of y divided by y. and then those y's cancel out, so that just leaves you with the natural log of y. That will be the new upper bound. The upper bound in terms of u is the natural log of y. Then inside the integral, we are replacing this power with u, so we do have e to the power of u, and then that will be multiplied by xy dx, which we are replacing with du divided by 2. But I will pull out that 1/2, so we have this multiplied by 1/2 du, and then don't forget about that dy for the outer integral. Okay, but now that entire inside integral is in terms of u, so now we can integrate and evaluate at those bounds of integration, and the integral of e to the power of u is just itself, so here's what we get. This is equal to the integral from 1 to 4 of 1/2 times e to the power of u, evaluated from 0 to the natural log of y, and then that's multiplied by dy. So now we want to plug in the natural log of y in for u, and then subtract plugging in 0. Doing that, we will have that this is equal to the integral from 1 to 4 of 1/2, I'm going to pull that out, multiplied by e to the power of the natural log of y minus e to the power of 0. All right. Now, e and the natural log are inverse functions, so they will cancel out, just leaving you with this y, and then e to the power of 0 is 1. So simplifying, we get this. It's equal to the integral from 1 to 4 of 1/2 times y minus 1. And then that's multiplied by dy. Okay, and really you could pull that 1/2 outside of the integral. I'll do that here. You'd have 1/2 times the integral from 1 to 4 of y minus 1. And again, e and the natural log cancel out, so that y comes down, and you just have y minus 1. And now we have a very basic definite integral that we can evaluate. We are integrating y minus 1 with respect to y. You will get this. You'll have 1/2 times 1/2 y squared minus y, evaluated from 1 to 4. Okay, so now let's evaluate this at 4 and subtract the evaluation at 1. This is equal to 1/2 times 1/2 times 4 squared minus 4 minus 1/2 times 1 squared minus 1. Now let's simplify. 4 squared is 16 times 1/2 is 8. 8 minus 4 is 4. So you have 4 minus 1/2 times 1 squared. That is just 1/2 minus 1. That is negative 1/2. So you have 4 minus negative 1/2, which is 4 plus 1/2, meaning that this is what we have. This is equal to 1/2 times 4 plus 1/2, and 4 plus 1/2 is 9/2 times 1/2 is 9/4. So this is equal to 9/4, which is the evaluation of this double integral. Okay, let's take a look at one more example for this video. All right, so for our last example, we want to evaluate this double integral. We have the integral from 1 to 3 of the integral from 0 to y of 4 divided by x squared plus y squared times dx dy. And so looking at this double integral, for the inside integral, we will be integrating with respect to x, since dx is listed first, and then for the outside integral, we will be integrating with respect to y. So these bounds of integration are values of x, and these bounds of integration are values of y. And so let's work on integrating this expression with respect to x. There is an x in the denominator. We have 4 divided by x squared plus y squared. So again, this is not just a simple case of a constant whose integral is that constant times the variable of integration. We do have the variable of x, the variable that we are integrating with respect to, within the expression. So we will have to use some other integration rule here. And at first that seems pretty tricky, but you want to try to remember some of your integration rules from Calculus 1. In particular, this expression corresponds to an expression that we know integrates into the inverse tangent function. And here's what I'm referring to. Remember this from Calculus 1, the integral of 1 divided by a constant a squared plus u squared, where u represents some function of x. The integral of that with respect to u is equal to 1 divided by a, the constant, times arctangent, the inverse tangent function, of u divided by a plus c. Now we're not really worried about the plus c part, we're more so worried about how this expression is integrated from this expression, because this matches up exactly with what we're dealing with here. Because again, remember, we are integrating with respect to x, so we are treating y as a constant. So in this denominator here, we do have an expression of x squared plus a constant squared. Exactly what you would expect to see in the denominator of this expression that integrates into the arctangent function. U squared is representing the x squared part, and a squared is the constant being squared. So in this case, we would say that u is equal to x and a is equal to y. And it doesn't matter that we have this 4 up top. You could pull that 4 outside and multiply it by 1 divided by that expression, and you still have this expression that integrates into the arctangent function. So don't let the 4 trip you up. We can deal with that. So let's actually integrate this using this rule. This will be equal to the integral from 1 to 3 of 1 divided by a, where a is the constant. So in this case, that would be y. So we have 1 divided by y times arctangent of u divided by a, so that would be x divided by y in this case. And then we don't need to plus c because this is a definite integral, but it will be evaluated from 0 to y, and that's still multiplied by dy. Okay, and that's pretty much it. Just don't forget about this 4. You do want to multiply that by this expression, so let me add that in here. We do have 4 multiplied by 1 divided by y times arctangent of x divided by y. Now let's evaluate. Let's plug y into this expression and then subtract plugging in 0. And we will be plugging both of those bounds in for x because we did just integrate with respect to x. So don't plug y and 0 in for y, plug it in for this x. Doing so will give us the integral from 1 to 3 of 4 times 1 divided by y times arctangent of x divided by y, which will be y divided by y, and then you'll be subtracting that expression, but where this x is replaced with 0, so you'll have 0 divided by y, which is 0, and arctangent of 0 is also 0, so that whole expression would be 0. I'll just write that like this. We are subtracting 0 and then multiply by dy. Now what's interesting right here is y divided by y is equal to 1. So really what we have here is that this is equal to the integral from 1 to 3 of 4 times 1 divided by y times arctangent of 1. And then that's multiplied by dy. And arctangent of 1, we can actually evaluate that. Arctangent of 1 is equal to pi divided by 4. So continuing our work up here, this becomes the integral from 1 to 3 of 4 times 1 divided by y times pi divided by 4, and then that's multiplied by dy, and these 4's will cancel out. 4 divided by 4 is 1, so the only constant that we're left with here is this pi, which you can pull out to the front of the integral, and this is equal to pi times the integral from 1 to 3 of 1 divided by y dy. And we know that the integral of 1 divided by y is a natural log of the absolute value of y. That's using the log rule of integration from Calculus 1. So integrating, we get pi times the natural log of the absolute value of y, evaluated from 1 to 3, but both 3 and 1 are positive, so when we plug them into the natural log of the absolute value of y, those absolute value bars are not necessary. This will just be equal to pi times the natural log of 3 minus the natural log of 1, but the natural log of 1 is equal to 0, right? This just becomes 0. So the final answer is just pi times the natural log of 3. So let's write that down. This is equal to pi times the natural log of 3, which is the final answer to this example. That is the value of this double integral. And if you want the approximate value, if you put that into a calculator, is 3.45 and some more decimals. But generally, you do want to give your answer like this. Okay, but with that, that is it for this example, and this was also the last example for this video. But if you do want to get some more practice evaluating double integrals, I do have more examples available on my membership site. So if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.